Thank you, Giovanni, for the invitation. I'm very happy to talk to you about our most recent results on the synchronized spin-Hall nano-oscillators, where we have included Memristor functionality. And I want to highlight and thank our collaborators in Sendai, Tohoku University, Shunsuke Fukami, Shun Kanai, and Hidiono, and at the AGH University of Science Technology in Krakow, Poland, Jakub Brzezinski, and then my group members at University of Gothenburg. So I'll first give you a background. Let's see if this moves. I'll describe the type of spin-Hall nano-oscillators that we use, and then how we use them to demonstrate synchronization in chains. And then we did this also in two-dimensional arrays. In both these cases, all the oscillators we're trying to make all the oscillators identical, and we're driving them with a single drive current, either through the chain or through the whole array. But that means we can't have individual control. So for that, we developed voltage gates on top of them. And we showed that we can indeed control both their frequency and their threshold currents using voltage-controlled magnetic anisotropy. What I will show today, this will then be the background, but what I will show today is that we can incorporate Memristor functionality in that gate. And that leads then to a non-volatile storage of the behavior of the oscillator underneath that gate. And that can be used for different types of computing. In particular, it provides you a way to sequentially go through a large array and just store a behavior or store a coupling, for example, instead of having to maintain it with voltage on top of all gates. So this non-volatility brings you a great deal of flexibility and brings you a great deal of energy efficiency. And then towards the end, I also want to mention some work we've done on spin-Hall nano-oscillator Icing machines. So the first baby steps towards that. The basis for all this is the spin-Hall effect. Just a very brief reminder that it's a phenomenon that converts an unpolarized charge current into a pure spin current transfers to that charge current. So for example, in our case, we use platinum or tungsten as the heavy metal layer, with a spin-dependent scattering, such that when we pass an electron current through that layer, we set up a spin imbalance across the top and bottom of that layer. And then if you put the ferromagnetic layer on top of that or beneath it, you can inject spin currents into the ferromagnetic layer. And then depending on how you apply the field, that is the orientation of the magnetization of the ferromagnetic layer, you can exert a torque that can be anti-damping or damping. But the interesting case is the anti-damping torque, because at sufficient current densities, you will be able to overcome the local spin wave damping, and that sets up an auto-oscillation situation of the local magnetization. And that's the whole basis for the spin-Hall nano-oscillator functionality. So for example, different groups use this now for quite some time ago. Cornell used a nanopillar magnetic tunnel junction and a continuous extended tantalum layer underneath, and were able to show that they could switch the free layer of that tunnel junction and also sustain some dynamics in the free layer. Then more dedicated experiments to spin-Hall nano-oscillators were done in metal systems with nanogaps by Demidov et al. And then the same group did also nanoconstrictions a few years later, and nanowires have been demonstrated by Krivorotto's group, for example. And I will focus on the nanoconstriction. It has a lot of good things going for it. The fabrication is straightforward. You need a bilayer, typically, and you only need to make a constriction or nanoconstriction, that bilayer. Anything from 20 to 300-400 nanometers will work, and that gives you a lot of flexibility in terms of material combinations and geometries, and it's all quite straightforward to fabricate. Since you have metals and preferentially you grow this on a substrate that has good heat conduction, you don't have any issues with with substantial joule heating, you can handle it. And then more interestingly, you have direct access to the dynamical region from the top. That gives you optical access, but it also gives you the possibility of putting down gates on that region. So that's what we have. Both of these things we use to both learn and to control the spin Hall nano-oscillator. So the first demonstration of a nanoconstriction oscillator was done by Demidov and Rushtin and in Democritov's group in Münster. And they showed both electrically and optically using a Burial light scattering microscope that indeed you can set up microwave signals, microwave auto oscillations of the local magnetization at microwave frequencies. And they show that in in-plane fields, this auto oscillation is a localized spin wave mode. So which can be beneficial if you want to have low threshold currents. But since we wanted to make synchronized arrays, chains and arrays, the strong localization makes the mode very small. So it doesn't talk well or interact much with neighboring auto oscillators. So for that, you would like a more extended mode. And it turns out that if you put the same system, same device in an out-of-plane field, you can get a whole range of different behaviors. And one is that this strongly localized mode, which is at one of the edges of the constrictions, will start to move into the center and start to expand into the center of the constriction. And then if you drive it with a stronger current, as is simulated here at the top, you will also get the movement away from out of the constriction. So this mode volume here, or mode area, is can be an order of magnitude bigger than the most localized mode in the same device. And that provides for interactions with neighboring oscillators, both through direct exchange, but also just because dipolar coupling will be more efficient when the auto-oscillating regions will be closer to each other. And that can be directly seen in pairs of oscillators. First, we just confirm here that this non-monotonic dependence of the frequency versus current is indeed there. But as I was saying, it's more important now that it's quite dramatic, I would say. You get very strong synchronization thanks to this mode expansion. So during this branch here, what you see are two microwave signals. And during this branch here, you're still in the edge mode behavior. But then as you turn around, this is where the mode starts to expand inwards, fill up the constriction. And then you can see that about here, the two of both signals become more fuzzy, and that's a sign of them interacting. And then also the frequencies approach each other, which is also a sign of frequency pulling. They start to approach each other's frequencies, and then at some point they snap together and decide to be completely on the same frequency, and they are now mutually synchronized. And from that point on, they have a much higher power because they are no longer fighting each other, and they are filling up both of their constrictions and generating a lot of much more microwave signal power than when they were on their own. We can expand this to longer chains. So here's an example of 9 such chains, and the longest we've fabricated is 50. And we have solid or robust synchronization, at least in chains of 20, and probably some things start to happen after that, but that's still being investigated. We have then expanded this into 2-dimensional arrays. And here I start with the smallest such array, a 2x2 array, where we varied the size of the constriction from 50 nanometers to 220. And we varied the separation from 100 nanometers to 300 nanometers. And in all these cases, you see that they fully synchronize. They're just one signal at the end. When we have 300 nanometer separation, you can see that there are individual signals at the low current end. But when you put them more closer to each other, it's harder to see that. Maybe they are indeed here when they are fully localized, but they do synchronize earlier when when they're closer to each other. But all 4 of them do synchronize in a 2x2 array. If we expand this to a 4x4, so we have 16 oscillators, that is no longer true for the largest separation. So here at 300 nanometers, we see 4 distinct signals instead. And those are actually the chains that are mutually synchronized inside themselves, but not synchronized with their chain neighbors. And if we put the chains closer to each other, 200 nanometers, we can see the individual chains here, and then they snap together as a signal. And then if we go further down, it's hard to see any individual signals. So maybe they are actually synchronizing from the beginning of very early on, when they just start to expand into the constriction. We can continue this to larger and larger arrays. And if we look at the microwave properties of the 5x5, 6x6, and 8x8, and 10x10, we can see that the 5x5 look very much like the 4x4. The 6x6 have problems at both 200 nanometers and 140 nanometers, but they fully synchronize at 100 nanometer separation. Same thing for 8x8. They don't fully synchronize here, but they do fully synchronize when they are 100 nanometers apart. And then when we look at 10x10, they do not fully synchronize. And this is to be expected. The more oscillators you add to the array, the greater the chance that they will break up into separate, partially synchronized regions, especially since we are primarily dominated by nearest neighbor coupling. This will indeed become the result. So to get even better synchronization after this, we should still shrink the separation and strive for even closer behavior or more similar oscillators, less distribution in their properties. When we look at the line width and the power and the peak power, they improve with the number of synchronized oscillators. So for example, the green data here are for the smallest devices, 50 nanometers separated by 100 nanometers. And in this case, we have oscillators synchronized all the way from 4 to 64 oscillators. So we can see that the line width drops as inverse to the number of synchronized oscillators as expected, and that gives us a line width of 60 kilohertz at 10 gigahertz operating frequency, which is a quality factor, if you like, 170,000, the frequency over the delta frequency, which is then an order of magnitude higher or better than any other coherency reported. So clearly, being able to synchronize more oscillators will improve the signal quality. Now, as I said in my introduction, we have no way of controlling individual oscillators in those arrays. For that, we developed a gated device. This was done by Himanshu Fulara and Mohammed Saidi-Nejad in the group. Just very briefly, I will summarize this as what we could observe. We could see that by changing the voltage from -2 to +2 volt on the gate, we could change the frequency about 40-50 megahertz. And that comes from the fact that the cobalt iron boron layer, in this case, when it's sandwiched between a tungsten and an MgO layer, has significant perpendicular magnetic anisotropy, and you can tune that through the voltage-controlled magnetic anisotropy effect. That was what we hoped to do, but we saw something else as well, and that was that the threshold current improved when we increased the voltage. So then this is a rather strong change. This is a 20% variation of the threshold current as a function of gate voltage. So we have two ways of controlling now individual oscillators. We can change their frequency in an array, or we can also change whether they should be on or off in the array, which we didn't expect. But we looked further into that, and that turned out to be that the effective nano-oscillator damping in this geometry will have a strong dependence on the anisotropy. And that's because if you look at the mode, how it behaves, to the left here we have STFMR measurements, and you can maybe see by eye, that the top curve here is broader than the bottom one. So there's definitely a change in line width when you change the voltage, and that can be analyzed as a change in the damping, which you can see here. So that's a 40–50% change in the damping, which is very large. And it comes because of the fact that the mode for this device, choosing a particular PMA value, we can stay at the border between propagating spin waves and localized. So, and that leads to a big difference in how strongly this mode is loaded by dissipation, or how much dissipation it exhibits. So when it's a big mode volume, it will, and when it's almost propagating, it will experience much more dissipation. And that's what happens when it's extended like this at -3 volts. Then we have a high effective damping of the device. And then when it's more contained, it interacts less with the far field, and it still has the same drive. It's still being driven by the same current. So it feels less dissipation with respect to how with the spin Hall drive it has. So that leads to a much lower dissipation. So it's a combination of a minor change of M effective and a bit of an amplification effect from the geometry that leads to this rather large change in effective damping. Now we'll come to the most recent results, and what I just showed with the individual control can be drawn like this. We have a device which we use in a pure voltage regime. So it's an E field governed change of the anisotropy in the cold iron boron. But this element here can be given memristor functionality. So in this pure voltage control, it's actually a memristor in its high resistance state. So it's about 1 gigaohm, and there is a very small leakage current going through it, and we control the device through the voltage only. But if we apply a stronger voltage, we can make ions move in this insulator, and then we can get a conducting path. We can switch the memristor to a low resistance state, and that resistance state can be now orders of magnitude lower, about 5 orders of magnitude lower, I think, than the high resistance state. And not only that, by changing the voltage or how you move these ions through your programming step, you can get them to move different amounts. You can tune the actual resistance that this memristor will now have in its low resistance state. So if you drive a current through the spin Hall nano-oscillator from source to ground here, and you have the possibility of putting a voltage on top of this now resistor, you will add drive current to it. And you can add negative voltage, then you will sink current instead through here. So you will reduce the drive current. So you have a change now of tuning, not through the field, but through the current that you can add to the device. And here is an example of such a gate, how it depends on voltage. So I'm showing the current through the memristor as a function of the voltage on top of the resistor. And here's 0, and here is 0. So if we follow the green line first, this is the gigaohm state, roughly. And then we come to here, to this point, and it switches to a level that we limit. So we limit this. We put a current compliance on to 100 microamps, and this will limit how much this conducting path can grow. You could have done it differently. You could use maybe pulse length or something else, but in our case, we use the current compliance of a voltage source. So the resistance of the device has actually switched to 15 kiloohms. So if we trace back the voltage to this point here, we will get a linear behavior within this once we get below the compliance. So here is a 15 kilo ohm resistor behavior, just linear, until we come to a point where we reset the device. And then the ions decide to move back, and we get back to a very high resistance state. If we change the compliance, let's say we change it to 10 microamps, then we will follow the red curve here. The switching distribution can be very big, actually. So these are not particularly high quality memristors, but it decided to switch here. And we had a current compliance of 10 microamps. So now the resistance became 43 kilo ohms instead. And so within this region here where we can operate, we can set different resistance values of this gate. And since we're controlling the oscillator now with the current, we actually have a multiplication functionality in this range here. We can set the resistance to a value between 15 and 43 kilo ohms, and then we can use within this region the voltage to generate a current that would be a multiplication between the voltage and the conductivity of the memristor. Or you can view it as you now have a non-volatile local memory added to each spin-hole nano-oscillator in the chain or in the array. And the impact this has on the device is the following. Here we see how the SHNO is voltage controlled. This is the high field regime. Then the memristor switches, and we get into a state here where we add current to the device. So in this case, we add 100 microamps to the device. So the frequency jumps up. Then when we trace the voltage back, we see no change during the compliance region, and we see a linear change of the frequency in this linear change of the resistance, of the current. And then we have a reset event, after which we have an electric field behavior. So we can we indeed have a way now of controlling the oscillator only by field if we want, or by added current through the device. We can do this on chains. So here is one of the simpler chains we made. So first we look at the behavior of this chain when the gates are floating. So there's no voltage, or they're not grounded either. And we pick out an operating point here that we will use. So this is a synchronized state of the two oscillators, and we're going to work here. And then we hope to be able to move the frequencies up or down by adding or subtracting current. And that is indeed what we see. We first can check that the memristor is behaving as it should. And then we can see that in the forward sweep, when we apply a negative voltage, this is the electric field that is changing the anisotropy such that the frequency 1 of oscillator 1 here will be different enough from frequency 2 such that they decouple. They are no longer mutually synchronized. But when we go back to floating or zero voltage, they synchronize again, and they stay synchronized until we have this memristor switching, and then they almost stay synchronized again, but at a higher value. So it's both of the oscillators will feel the same additional current, ideally, and hence they are almost staying fully synchronized, although there might be some variation here. If we trace it back, we see that they are dominantly mutually synchronized, but it becomes better once we get to slightly lower added current, and we then have a linear frequency dependence on the voltage here until we get to a reset event. And so with that, we can control also the synchronized state of the two oscillators. We can see that it's synchronized as a function of the voltage, because we can look at the peak power and the line width. And before I end, I want to jump a little bit to spin-hole nano-oscillator Ising machines and what we've done there recently. So Ising machines may or may not be well known. It's actually what D-Wave uses in their quantum annealer. It's the Josephson junctions being coupled together and interacting, and they can tune the coupling strength, and they can set up what is called an Ising machine to solve combinatorial optimization problems. One can show that this can be done with classical oscillators as well. And D-Wave may or may not have a quantum advantage, but they claim that they use quantum annealing to reach their solution faster. But you can use other annealing schemes in classical oscillators being coupled together, as long as you phase binarize the oscillator. So you enforce a frequency onto your oscillator array such that they will be injection locked. And if you put them, if you injection lock with twice the frequency, you have two generate states. The two oscillators can decide to injection lock in phase with respect to the fundamental frequency, or out of phase with respect to the fundamental frequency. And that is something that we have started to investigate. So we take this 2x2 array, where we will have coupling between all four of them. If we injection lock them with a fundamental frequency, we will get the trivial result that they all want to stay in phase with this signal, and hence in phase with each other. But if we injection lock them with twice the frequency, there's the degeneracy. So now they can decide to be since they're at half the frequency of that 2f, if you like, with respect to each other, they can decide to be in phase or out of phase. And now if they have coupling, let's say they preferentially would like to stay out of phase with each other, then you would see such states. So if you can now control the coupling strength and coupling sign between different oscillators, you can use them, you can use the behavior of this oscillator network to solve combinatorial optimization problems. And that's a much bigger topic, but that's essentially the fundamental mechanism behind the Ising machine. So we looked into that. We started with 1x2 arrays, so we just have two oscillators in parallel. We injection lock them with twice the frequency. They start out in a synced state, and it just means that they are mutually synchronized to each other, and they are relatively in phase, I would say. But they might have some relative phase with each other, which we cannot really determine or measure right here. But when we injection lock them, that happens here. So this is the power of the injected signal. And if we increase the injection locking, we can see that two different states are showing up. So here you can maybe slightly see it, that the power spectral density changes. If you look at the peak power, there's definitely two well-defined states showing up, and they are diverging from each other. So one is becoming stronger and the other one is becoming weaker, and we identify that as the two oscillators being in phase and the weaker one with them being out of phase. And this is a logarithmic scale, so there's a factor of 2 or so between those two powers, and that increases. The line width doesn't change much. They are just as happily synchronized or injection locked, but the power out from the array changes significantly. You can do that differently by having an injected power and then changing the frequency. Here they didn't start out mutually synchronized. But they snap together when the injection frequency is close enough to them, and then you can see that there's a high power state here, which corresponds to in phase, and a low power state here, which corresponds to out of phase. And we can see this microscopically if we use phase resolved BLS microscopy. So we take a BLS microscope, and we use the signal that we injection lock the oscillators with to time to bin out when we collect photons from the detector, and then separate. Then we can say when in which phase we detected the spin waves. And when we do a line scan across this array, and we then look at the spin wave intensity, we can clearly see that this oscillator is in phase with the 90-degree reference in this case, and this oscillator is not. If we change the reference 180 degrees in the detector, we then see that we have exactly the opposite situation. So this is an anti-parallel state. When we put the array in a parallel state, we instead see that both oscillators are indeed at the same phase, and none of the oscillators show up at in the 180-degree phase. So they are quite closely anti-phase and quite closely in phase in both these cases. We can extend that to 4 arrays, and we'll just wrap up now. But long story short, we see more or less the same behavior. But here we can get more states. So we think we have an all in phase state. We have one intermediate where one of the oscillators are out of phase, and then we have a very low power one where we have them where they almost cancel out each other completely. There are 2 are up and 2 are down, and we can see that also when we change the frequency. And with the BLS microscope, we indeed can confirm this electrical measurement. When the reference is at 90 degrees, we see that oscillator 2 and 3 are at the same phase, and oscillator 1 and 4 are at the same phase. So they prefer to couple in phase, whereas they prefer to couple anti-phase with in between themselves this way. And when we reverse the reference, we indeed see that they also reverse sign. When we get completely in phase electrical signals, we also see that the array is also completely in phase. So with that, I thank you. And so I hope I have shown to you that we can get Memristor control of this mutual synchronization, and that we have taken the first steps towards possible spin-Hall nano-oscillator Ising machines. So thank you for your attention.